Welcome to the fundamentals of biomolecules. Today, we are going to explore one of the most fascinating and crucial topics in biochemistry, the concepts of Km and Vmax. If you have ever wondered how our bodies process food, how medicines like cholesterol drugs work, or how enzymes function as microscopic machines, you are in the right place. We will build this from the ground up, so even if you are completely new to enzyme kinetics, you will understand exactly how these molecular engines operate. Let us dive in. To understand how enzymes work, let us imagine you are managing a busy coffee shop with exactly one highly skilled barista. In this scenario, the barista represents our enzyme, the coffee beans are the substrate, and the finished cups of coffee are the final product. When there are only a few orders, the barista works at a relaxed pace. But as more customers pour in and the pile of beans grows, the barista must work faster and faster to keep up with the demand. This simple physical picture perfectly mirrors how enzymes behave in our cells when they encounter varying amounts of substrate. Building on our coffee shop analogy, there comes a point where our barista reaches their absolute maximum physical speed. Even if you dump a mountain of coffee beans on the counter, they simply cannot make coffee any faster. In biochemistry, this absolute maximum speed is what we call Vmax, or maximum velocity. It occurs when every single active site of every enzyme molecule in the solution is completely saturated with substrate. The enzyme is working at its absolute peak capacity. Adding more substrate at this point will not increase the reaction rate because the microscopic machines are already operating at their physical limit. Now that we understand the absolute speed limit, we need a way to measure how efficiently the enzyme reaches that limit. This brings us to the Michaelis constant, known as Km. By definition, Km is the exact substrate concentration required for the enzyme to work at exactly half of its maximum speed. It is a direct measure of the enzyme's affinity for its substrate. A low Km means the enzyme binds the substrate very tightly and reaches its maximum speed quickly. Conversely, a high Km means the enzyme binds weakly, requiring a massive amount of substrate just to get going. You might be wondering why these two parameters matter outside of a textbook. Understanding Vmax and Km is absolutely critical in fields like pharmacology and medicine. When scientists design a new drug, such as statins to lower cholesterol, they are often creating molecules that alter the apparent Km of specific enzymes in the body, effectively slowing them down. Without knowing these exact values, doctors would have no way to calculate the correct dosage of medications. Furthermore, industrial engineers use these parameters to optimize conditions for producing biofuels or brewing beer, ensuring enzymes work at their most efficient rates to save time and money. Now that we have established the concepts, let us look at the mathematical relationship that ties them all together. This is the famous Michaelis-Menten equation. It conceptually originates from the idea that reaction speed depends on available substrate, but is fundamentally limited by the enzyme's maximum capacity and binding affinity. In this formula, V represents the initial velocity of the reaction. Vmax is the maximum possible velocity. The letter S in brackets stands for the concentration of the substrate, usually measured in moles per liter. Finally, Km is the Michaelis constant. If you increase the substrate concentration to a very high level, the denominator becomes roughly equal to the substrate concentration itself, and the overall velocity approaches Vmax. Let us put this formula into practice with a straightforward laboratory scenario. We're given an enzyme with a known maximum velocity of 100 micromoles per minute and a Michaelis constant of 2 millimolar. We are asked to find the exact reaction velocity when the substrate concentration is exactly 2 millimolar. We chose the Michaelis-Menten equation because it directly connects these known variables. We substitute 100 for Vmax, 2 for the substrate concentration, and 2 for Km. The numerator becomes 200 and the denominator becomes 4. Dividing these gives us a final velocity of 50 micromoles per minute. Physically, this means the enzyme is operating at exactly half of its maximum capacity. The example we just solved perfectly matched our physical interpretation. But let us prove mathematically why this always happens. We're setting out to prove that when the substrate concentration equals Km, the velocity is always exactly half of Vmax. We start with the standard Michaelis-Menten equation. Our first mathematical step is to substitute the variable Km in place of the substrate concentration, S, wherever it appears in the formula. This substitution represents the specific physical condition we want to test. By doing this, we set up the equation to reveal the exact relationship between the initial velocity and the maximum velocity under these specific conditions. Continuing from our setup, let us look at the denominator. We now have Km plus Km, which simply adds up to 2 times Km. Our equation becomes Vmax times Km, all divided by 2 times Km. Because Km appears in both the numerator and the denominator, and it represents a non-zero concentration, we can mathematically cancel it out. This leaves us with our final result. The velocity equals Vmax divided by 2. This beautifully proves our initial concept. The intuition here is that the mathematics perfectly mirrors the biology. Km is indeed the exact substrate concentration required to reach half maximal velocity. Now that we have proven the theory, let us tackle a real-world medical example involving 2 different enzymes processing the same liver toxin. Both enzymes have a maximum velocity of 120 micromoles per minute. The toxin concentration is very low at 0.5 millimolar. Enzyme A has a Km of 0.5 millimolar. We need to find its velocity. Because the toxin concentration exactly matches the Km of enzyme A, we do not even need complex math. Based on the proof we just completed, we know immediately that enzyme A will operate at exactly half of its maximum velocity. Half of 120 gives us a final answer of 60 micromoles per minute. Let us continue our comparison by calculating the velocity for enzyme B, which has a much higher Km of 10 millimolar. The given toxin concentration is still 0.5 millimolar. Because this concentration is much lower than its Km, we must use the full Michaelis-Menten equation. We plug in 120 for Vmax, 0.5 for the substrate, and 10 for Km. The numerator becomes 60, and the denominator becomes 10.5. This setup shows how the large Km value dominates the denominator, pulling the overall velocity down. Dividing 60 by 10.5 gives a final velocity of approximately 5.71 micromoles per minute. Physically, this shows enzyme B is barely working compared to enzyme A. To visualize everything we have calculated, let us look at the Michaelis-Menten saturation curve. On the horizontal axis, we have the substrate concentration, and on the vertical axis, we have the reaction velocity. Notice how the curve starts steep, but eventually levels off into a horizontal plateau. That flat line at the top represents Vmax, the absolute speed limit where the enzyme is fully saturated. Now, look at the dashed line marking exactly half of Vmax on the vertical axis. If you follow that line to the curve and drop down to the horizontal axis, you hit Km. This diagram beautifully summarizes our entire lesson, showing exactly how substrate concentration drives velocity until the physical limits of the enzyme are reached. We have covered a lot of ground today, so let us reinforce the three most important pillars of enzyme kinetics. First, Vmax represents the absolute speed limit of an enzyme when it is completely saturated with substrate. Second, Km is the exact substrate concentration required to reach half of that maximum speed, serving as a perfect indicator of binding affinity. Finally, a lower Km means a higher affinity, making the enzyme far more efficient at low substrate concentrations. By mastering these concepts, you now have the tools to predict exactly how fast any enzyme will work, whether in the human body or in a laboratory. Great job following along.